At 22, chapter 11 still. This is an epoxide problem. And in there you have CHO3 and then H2SO4. So you got to recognize essentially your reagents. Right? So you recognize their epoxide, and you know the epoxide. In some cases, it can be the nucleophile first. In some other cases, it can be the electrophile first, right? These carbons are electrophilic, carbon 1 and 2, let's say. So if you're not sure about the epoxide, you should look at the reagents you have here. So what do we have here? We have methanol, solvent, even though it's on the top part of the arrow, that's the way they drew it. Bottom part, you have H2SO4. What's H2SO4?
It's an acid.
Yep. And what you do with acids, the strong acids, you want to use it to react first right away. So it's
throwing me off there.
Yep, it'll throw you off. It's basically H plus.
Okay.
So if you have H plus, right? If you have a reactive acid, make sure it reacts. See the lone pair here attack. So we're doing the epoxidate. We're reacting on epoxide in acidic conditions. And once we're in acidic conditions, which carbon do we want to attack? Carbon 1 or carbon 2? In acidic conditions, how do we decide which carbon to attack?
Be the more substituted.
The more substitutes, so that's going to be which carbon?
Carbon 1.
Carbon 1, that's right. So it attacks carbon 1. Electrons go up. This is a trans addition. Alright, CH3 is still there. The H plus is actually a catalyst, even though they don't tell you that. It is a catalyst. So the final step is these electrons and this hydrogen going back to the oxygen, which gets us to our final product where the new ether is formed. Trying to kind of differentiate between how do we approach these problems, right? So let's look at the same starting material. We'll use the same starting material. And we'll react it with different reagents and see how that process goes. So this same starting material, I'm going to do it 3 times. Well, I'll just do the first one. The first time we're going to have this alcohol. So the first question we ask ourselves is what kind of alkyl leaving group do we have? So what kind of alkyl leaving group do we have here? Primary, secondary, tertiary, allylic, benzylic, secondary. We got a secondary one. Good. So.
Wait, sorry, I didn't mean to interrupt you. But when it's on a ring like this, what is it classified as? What's the...
Still secondary. Still secondary.
It's just secondary?
Yep, just secondary. Nope, doesn't matter if it's on the ring, just secondary. So.
Okay.
Right, so E2s you need that antiperiplanar thing, which is a whole other deal.
Yeah.
But.
And so, so there's primary, secondary, tertiary, and then there's allylic and benzylic.
That's right.
Benzylic is naturally on a benzene ring.
1 carbon off of the benzene ring. So the allylic is.
So it's on the benzylic carbon.
Benzylic carbon.
Okay.
Yep.
And then allylic
is 1 bond away from the pi bond. Just 1 pi bond. That's an allylic position.
Okay.
Yep. Okay. So secondary alcohol. So unlike secondary alkyl, so unlike halogens, right? Bromine, chlorine, iodine, when those are leaving groups, those do not just leave for secondaries, right? We've seen we can form secondary carbocations if we have a really good leaving group. So really only water or those alcohols or the ethers. So when we react this with HBr, the first step is going to be HBr as a reactive acid. We're going to protonate that water. So we say 1, 2. So we've generated water, or water as a leaving group here. And because water is such a good leaving group, even though it's secondary, what's going to happen? It's going to form a carbocation. Right? So we can form secondary carbocations when we have really, really good leaving groups, things like water. Alright? So we're going to form a carbocation here. what do you guys know about carbocations? What will they do? They will rearrange. Notice, right, once I have a carbocation, there's no longer wedges and hatches because that carbon's sp2 hybridized, so it's flat. So I have a secondary carbocation here. What kind of rearrangement should I do?
Hydride shift.
Hydride shift from which carbon? Carbon 1. Good. So there's H's there now. And now here's the plus charge. And notice again, no more wedges and hatches, right? And all along the way, I haven't drawn it in, but Br minus has been here all along the way, right, to balance our charges out.
So does that, when carbon 2 go back to wedge? I mean,
Well, it would go back to wedge and hatch, but it doesn't matter, they're both H's.
True.
So, right? True. Okay, so now bromine, now you gotta make a decision. Is this gonna do, so now we have a carbocation. So what are possibilities for what kind of reactions are possible here? SN1 and E1. So now you gotta decide, well, is Br minus more likely to act like a nucleophile, more likely to act like a base?
See,
What-
that confuses me when you.
So, well, let's think about how stable it is. Is Br minus reactive or not very reactive, relatively speaking? Right? So all the hierarchy of leaving groups we created, right? Water is a good leaving group, right? Is water, right? Water is not a very reactive thing, right? Why would bromine be reactive?
Minus.
Has a negative charge. Can bromine do resonance? No, right? So bromine Br minus is stable, but it's more likely to act like a nucleophile because it really can't physically spread the charge out, right? It can slosh the electrons around, but just in itself. It can't spread out like maybe like the tosyl leaving group could, right? There's no resonance to spread that charge out. So this is going to act like a nucleophile and do an SN1. So HBr, HCl, and HI do SN1s. And of course, since this is a carbocation, you'd make, right, it would attack me the top or the bottom there. Good. So HBr, we're going to get a rearrangement here. We're going to get SN1, and there's going to be a rearrangement. All right, the leaving group, right, we start out with our function group on carbon 2, and it ends up on carbon 1. So that tells us, right, carbocations, right? If it moved around, that makes me think of carbocations. Now, if we want to do an E1 reaction here, what we would have used H2SO4, and that would have given us an E1 reaction, right? Because the conjugate base of H2SO4 is not very nucleophilic because it has resonance and rather act like a base,
Okay, so.
right? So instead of having Br minus here, if we had this, right? If we had that, this guy would do an E1 in this case. Right? So that would be different. If I'd used H2SO4, I would have done an E1 instead.
And H2S sulfuric acid always does elimination.
This conjugate base does an elimination, right? There still would be a hydride shift. The hydride shift would still take place. But at this point, right, one of these H's would be taken away by this guy. At this point. The hydride shift would still occur. Okay. Take a look at that same starting material. And what's going to happen if that reacts with PBr3 in purity? So yeah, so now these activation of alcohol methods don't undergo carbocation formation, do they? So the first thing that happens here is our oxygen attacks, and we kick out a bromine. Pyridine comes along. Just have Br minus. At this point, I can show you have it so the Br minus is an SN2 attack, right? Because this is not that good of a leaving group. It's a good leaving group, but not as good as water. We do an SN2. And if we do an SN2, what happens to the stereo center?
Oh, it doesn't change.
SN2, it inverts, it does change. So now the H is going to be going back, and the thing we added, the Br, is coming out at us. And we lost OH, PBr2, and at this point the pyridine takes that H and makes a salt, and then that's our final product with the salt. So this one has an SN2 part of it. Different product then, right? If this is our final product right here, this is very different than the one we just did with HBr, right? HBr, if you're numbering these carbons 1 and 2 again, 1 and 2, 1 and 2, with PBr3, the bromine ends up on carbon 2, the same place that it started off with, where the OH was on. But what happened to the stereochemistry? It inverted, right? It inverted. Alright, one last one to look at. Same deal as before, same starting material. Now for this one, we're going to have a tosyl chloride. Pyridine again. And that's our step 1, and then step 2, they add in NABR. Okay. Again, the lone pairs on the oxygen attack the sulfur, kicks out the chlorine. I'm just going to abbreviate it as TS now, tosyl, just to shorten it. We made CO minus, that got kicked out. Methyl's still here, H is still there. Pyridine at this point comes in right away. Takes that H, I mean it could have gone first there. The thing that's special about tosyl is that tosyl doesn't have the SN2, right? This is not as good a leaving group as the one before, and so this chlorine will not attack. This will not attack. So we actually can make this and stop it. So it's a little different than the last one because we've activated the alcohol without having to do any subsequent reactions on that carbon attached to that alcohol. Right? This is carbon 1 and 2, 1 and 2, 1 and 2. We can stop right here. And we've made the tosyl, the O-tosyl, and this salt, which comes out of solution. So that finishes step 1, right? Step 1, right, when they have reagents that says 1 and 2, these reagents react with the starting material. These things do not react with each other. This finishes reacting with the starting material. When that's all done, then you go to step 2.
And the reason why chlorine just doesn't go ahead and attack is because the O-tosyl is
Not as good a leaving group as some of those other ones, right? That goes back to our leaving group hierarchy,
yeah.
right? And also because this becomes a salt, and this comes out of solution. So then once the Cl is mashed up in a salt pair, then it's stuck there. So then the final step here, you have Na plus Br minus. Well, now you can do the SN2, kick out the tosyl, and what do you end up with? Now what happened to the stereochemistry? The bromine should be wedged or hatched. Bromine should be
Or wedged. Or I don't know
wedged.
which one it is. Yeah, that one.
Yep, and that's there. So they end up doing the net SN2 after the fact. Good.
So the first step that it does is not considered anything.
It's just activating the alcohol.
It's just the activation.
Right, and the ones before you do the activation and then you do an SN2 all in the same pot, the same time. With the tosyl, you do the activation, then you stop. And then you have to add in whatever nucleophile you want. The other ones, you activate, and then the thing that you kicked off originally to activate comes back around and attacks.
What kinds of nucleophiles can you use in a tosylate reaction? Because obviously a chloride wouldn't work, right?
No, you could. You could use a chloride, right? So part of the thing is that this comes out of solution, right?
Okay.
So you could use you could shift, you could use excess chloride, you could use a lot of it, you could heat it up, you could use a lot of different things. A lot of these are carbon-based nucleophiles at this point they like to use.
Okay.
Right, so the tosyl is nice because you don't change the stereochemistry by adding it.
Yep.
The other ones you do change the stereochemistry once you add it. That's the nice part about tosyls.
Yeah. And then one more question. So that nitrogen is relatively negative, right?
Which one?
On the pyridine.
It has a lone pair that's not part of the pi system.
Okay. And so,
So it's relatively basic.
okay. So if it's relatively basic, how come Cl minus can form a salt pair with it?
Because it grabs this H, right? And now it has a plus charge.
Okay.
And then it comes out of solution. And then also pyridine is the solvent, so there's a lot of pyridine around.
Alright.
Good questions. So what does the tosyl look at like at the end? If I were to draw it out, let me draw it over here. It'll be O minus sulfur, then that benzene ring with the methyl on it, right? And this oxygen right here ends up being this oxygen right there.
Wait, say that one more time.
So this oxygen that started off as the alcohol ends up on the sulfur from on the tosylate, right? See how it attacks that sulfur originally?
Gotcha.
This oxygen is this oxygen. That's where it ends up. So something to keep in mind, let's not forget, if I took T-butanol, and I reacted T-butanol with HCl, I reacted T-butanol with HOSO4, so H2SO4. I reacted T-butanol with, say, PBr3, a little pyridine there. And then, heck, even one, why not just toss one more on here? What would happen if I reacted T-butanol with tosyl chloride and pyridine? What would be the products of those reactions? Okay, so for this one, so now we have all tertiary alcohols. We know with primary we can never form a carbocation, but with tertiary we know we can't do SN2. So that will change some of these other ones that maybe we've been doing SN2s with. So again, we attack. That would get us, and kick that out, that would get us to a water as a leaving group. These are all tertiary alkyl leaving groups. And normally we'd like to do a SN2 with it, or first we'd form the carbocation, right? So we'll form the carbocation. And now chlorine's there. Chlorine will act like a nucleophile. We'll do an SN1. Right? Easy, SN1. So that will make the tert-butyl chloride. Nothing too wild there. Again, with this tertiary alkyl leaving group, we'll make the carbocation, right? I'm going to skip a couple steps. You're believing me here, hopefully, at this point. And now we have the conjugate base of sulfuric acid. Now, this is not a very good nucleophile. This would rather act like a base. So we got to start looking for those beta H's. Grab one of those. In this case, we did a E1. And our final product here is the alkene. All right. H2SO4, the POCl3, they did the eliminations, remember. What about with PBr3? PBr3 now, usually these don't work very well with these, essentially they don't work very well with these tertiary alcohols because of sterics. And really these aren't very useful. Right, so I would almost say with these ones, I don't know if I wanna go all the way and say no reaction, but they're not very useful tertiary alcohols. The PBr3, the PCl3, the zinc Cl2, those aren't very useful with tertiary alcohols, because you can never do SN2s with those, right? So really, it's gonna be something like this, no reaction.
Okay, which ones did you say they would?
So the PCl3, PBr3, the SOCl2, and the zinc Cl2. Those four aren't that useful tertiary alcohols.
PBR3, PCL3, SOCl2.
And zinc Cl2. Yep, those four aren't very useful tertiary alcohols. They're just not very useful. Primary and secondary, they work better. Because sterics becomes an issue with some of those. Those are pretty big things. It becomes an issue.
Like a few minutes ago.
Yeah.
Now the tassel actually does work though. So the tassel you might think is big,
It is big, yeah.
but it's flat. It's planar, right? So it's a little different, right? PCl3 is in a pseudo-tetrahedral geometry, right? So it's a little more, it really is. If you look at it, S is flat, has those pi bonds. It's really kind of flattened out. And that benzene ring, you think that benzene ring's big, but remember that benzene ring is completely flat again. So it's really not as, it looks big, but it's not, in 3 dimensions, it's not that big. Whereas zinc Cl2, those are bigger, PCl3, 3 chlorines flying around, that's a little more sterically bulky than you realize. So a tassel though, what this is gonna do, which is nice, is again, you're gonna stop here. You made the O tassel. So you have activated it and you've stopped there. So now you can do an E2 reaction if you want to. Right? You can't do an SN2, but you certainly can do an E2. Right? Alright, let's do the leaving group hierarchy. So in the leaving group hierarchy, the best leaving groups are at the top, and the best leaving group we have so far has basically been water. Alright? Also a good leaving group is those alcohols, those ORs, OHRs. But really, right, the nice thing about these is they will form secondary carbocations. Will form with these as leaving groups, right?
So the alcohol can do it.
The alcohol can do it too. Yeah. So that'd be like the activation of an ether, right? You have an alcohol as a leaving group. So secondary carbocations will form with really, really good leaving groups. Oxygen with a plus charge, like the water or the ether, will work. One step below that is our zinc guy. Right? Not quite good enough for a secondary carbocation, but still good. Our O minus PBr2 and our O minus PbCl2. This is a second tier kind of group. And our other leaving group, remember, it was the SO2 and the Cl minus. Those guys were kind of combined together. That was a pretty good leaving group. But not good enough to make a secondary carbocation. But these leaving groups were good enough to do that SN2 all at the same time. Right? So SN2 takes place during activation. And the SN2 takes place during the activation of the alcohol with these leaving groups. And the SN2 will take place during that activation. So they're still pretty good, just not as good as water. Right? Not good enough to form a carbocation, but good enough to do the SN2 while the activation is taking place. Now one step below these guys is our tassel leaving group. Things of that nature. I think the other one we added in here was the OPOCl2. Good leaving groups, but not so good that they're going to do that SN2 during the activation. Right? So no SN2 during activation. So these guys can actually be isolated. You actually isolate these guys. Right? Also, something like the sulfuric acid cation, or the O, this guy. Something like this, right, will act like a base. Right? That'll act like a base. Because again, it's stabilized by resonance, so it's not that nucleophilic. It can be a base, but it's not that nucleophilic because of the resonance it can do. Right? So it won't act like a nucleophile. And then below all these guys, back to our old favorites, I minus, Br minus, and Cl minus. Now these guys act like nukes. Right? They're good leaving groups, but they're not as good as these other ones, right? All these other ones, these guys can do resonance. These guys form as a gas. An oxygen phosphorus bond is really, really stable. That's a really great bond to make. Water and alcohols are really stable things, right? These are good leaving groups, but it's just that these guys are better. So, right, these are big atoms that can slosh the electrons around in one place, like a lot of orbitals, so slosh the electrons around, spread them out. But these guys can actually do resonance, which is even better, right? It's a better way of spreading out over other atoms. Forms a gas, that's going to shift equilibrium. Or these guys form really strong bonds, right? They're really favorable. So that's why these guys are really good leaving groups. And now these guys, right, water and alcohols are just really stable molecules. No charges, they're just really happy, right? So that's kind of how it breaks down on why they're different levels.
Wait, can you repeat that part for the bottom half again?
So right, I minus, these guys are stable. They're just not as stable as all of these other ones, right? I minus can spread its electrons around, but just around itself, right? I minus is big and fat, and so it can move its electrons around itself. But resonance, right, these guys can do resonance, where they actually move the electrons through different atoms. So that's better. These guys actually form really strong bonds, right? Oxygen and phosphorus is a really strong bond, so that's really wants to happen. Or it forms a gas, which, right, once the gas goes out of solution, that's going to shift equilibrium. So it makes a gas is a really, really good leaving group. And then water and alcohols, right, are just really stable. But once they want to be not bonded to anything else, right? They're happy as water and alcohol, so that's why they're the top. Good.